Okay, so the next speaker is Pawan Kumar from University of Texas. And he's going to talk about fast radio bursts. So the floor is yours. We can see your screen, so everything.
Very good. So I would like to thank the organizers for inviting me to give this talk. I will start by providing a very brief summary of the relevant observations, and then half of the time would be spent on the physics of FRBs, and the remaining time will be on the probe using FRBs to probe cosmology. So that's the plan. I would start with the very basic, and that is that the dispersion relation for electromagnetic wave in plasma is given here. And much of the universe is plasma, which means ionized medium. The group speed of the electromagnetic wave is frequency dependent, and that group speed is larger at larger frequencies, so that the signals, if we take a short pulse of burst, the signal arrives first at highest frequency and with some delay at lower frequencies. And that delay in time with respect to infinite frequency is proportional to 1 over frequency squared. The magnitude of the delay is proportional to so-called dm for dispersion measure, and that's just the integral of electron density between the source and us. So it's the column density of electron between the source and us. The first fast radio burst was discovered in 2007 with the Parkes telescope in Australia. This is the signal many of you have seen. This signal, this is the roughly diagonal band is the signal. You can see x-axis is the time of arrival of the signal, y-axis is frequency. Very clearly you can see that the signal arrives at the highest frequency first and then at lower frequencies with this delay, which is 1 over nu squared delay. So that's the characteristic delay here. The duration of this signal was 5 milliseconds. dm in the astronomer's unit was 375 parsec per cc, and the contribution to the dm, to the electron column density from our own galaxy along that line of sight is 25 in this unit. And therefore, this object was concluded to be at a distance much larger than the size of our galaxy. From the mean intergalactic medium density, it was inferred or estimated that the distance to this particular object is 500 million parsecs. That's about a giga light years. The luminosity of this object was 10 to the power 43 arcs per second. That's 10 billion times brighter than the sun, and this is in the radio band. So clearly a very spectacular outburst. There was a period of confusion leading to a breakthrough. 16 more bursts were reported in 2010, same telescope in Australia. However, these bursts were detected in all 13 beams of the telescope, and that it strongly suggested that these things are not, these are terrestrial, not, the source is not outside of the planet. And many people suspected that the very first burst detected by Lorimer and collaborator was also not cosmological. They were dubbed Periton, or this mystical wind is tagged. Very clever detective work carried out by Emily Petrov, who was a graduate student at that time, established the origin of periton to be microwave, to be specific, premature opening of the microwave. Microwave leaks out, detected by the telescope. The breakthrough was that Arecibo detected a burst in 2012, and then a repeat activity from the same location was seen 3 years later. And that led to accurate localization and measurement of the distance. And it established that at least this particular burst is extragalactic and far away, cosmological, at a redshift of about 0.2. Furthermore, it also established, since you are seeing multiple bursts from the same source, that it is not a catastrophic event where the underlying object is not destroyed, but it lives to produce other bursts. Last year, on April 28, a burst was detected in our own galaxy. Now, this is the localization ellipse that you are seeing. It was detected by two facilities, STARE-2, which is a Caltech facility, and the Canadian CHIME. The Canadian CHIME localization is much more accurate than this STARE-2. And then inside of this CHIME localization, I hope you can see on your screen here a dot, and that's the position of a known neutron star with super strong magnetic field of strength 22 billion Tesla. And this object has a spin period. The neutron star has a spin period of 3 seconds and a spin down age of 4,000 years. So it's a young system, relatively young system. So which means that we have here, it established that at least one FRB is associated with magnetar. The energy output of this event was 2 times 10 to the power 35 arcs in the radio band, but a lot more energy came out in the X-ray flare. About 40,000 times more energy came out in the X-ray band. You can see the signal in the radio band here, de-dispersed, taking out that 1 over nu squared delay in the arrival time. You can see the signal de-dispersed as seen by STARE and then in CHIME. CHIME saw 2 pulses separated by 30 milliseconds. STARE saw 1. STARE has a frequency of a 1.4 gigahertz. CHIME saw between 400 megahertz to about 800 megahertz. And these 2 pulses, as I said, separated by 30 milliseconds. The second pulse is very nicely lined up with this at this higher frequency of STARE-2 observations. Here is a brief summary of the observed properties of FRBs. So at this point, more than 500 FRBs have been detected. 60 of them, at least, have repeat outbursts. The rate at which the rate of FRBs per day is estimated to be something on the order of about 1,000 bursts per day. These things have duration between 1 millisecond and 20 milliseconds. The flux could vary on a very short time scale of 10 microseconds. And as recently reported, just a couple of days ago, there was a burst detected in a nearby galaxy, M81, where the flux varies, has short spikes of duration, about 15 nanoseconds. And that suggests that the emission is produced, the photons are being produced in a very small region of size, roughly a kilometer, modulo the Lorentz factor of the outflow from the object. Some of the bursts are 100% linearly polarized, others no, not so highly linearly polarized. 9 FRBs have been localized, and they do not show evidence for large contribution to the DM electron column density from the source or the near vicinity of the source. And that suggests that most FRBs are not associated with very young supernova remnant or dense regions of the interstellar medium. Turning to the physics. The physics says that the FRB radiation, if we were to assume that it is an incoherent radiation, such as the radiation that we see from the stars, quasars, and so on, then the temperature that is needed to produce the luminosity we see in the radio at gigahertz would require a temperature of the source to be completely unphysical, 10 to the power 35 Kelvin. Yeah, that's completely unphysical. And that simply means that the FRB radiation, like the pulsar radiation, got to be coherent. And that simply means that electrons or particles which are doing the radiation, radiating radio photons, they are all radiating in phase, like the masers or the laser. And so the flux or the luminosity increases with the number of particles radiating squared. This is another way of saying this is that the number of photons in each quantum state for the FRBs, for the FRB radiation is of order 10 to the power 37 photons in every quantum state, which has interesting consequences regarding the physics and the radiation mechanism for these very bright radio pulses that we see in the following way. That these photons is scattered by an electron, that's the standard Thomson scattering, that cross-section is enhanced, the probability of this scattering rather is enhanced by the final, well, the occupation number of the final state. And if the occupation number of the final state is 10 to the power 37, well, that probability of scattering is enhanced. Not by this huge factor of 10 to the power 37, because there is an inverse process that nearly cancels this. So the effective enhancement to the scattering probability is more like a factor of a billion at a distance of about a AU, 10 to the 13 centimeter. And that means that there is a very strong radiative force in the source region because of the scattering of these photons by electron. And the plasma in the source region would be dispersed by this enormous radiation force, unless there is a mechanism to keep the source plasma confined. And that can be done either in the close vicinity of the neutron star or the magnetar at a distance of less than about 1,000 kilometers, where the magnetic field is very strong and that suppresses the scattering cross-section by a factor of the cyclotron frequency to the radio wave frequency squared. So that's one way that the plasma that is producing the radio waves can be confined, okay, for a millisecond or a few milliseconds to produce this strong radiation. The other way is that you produce the radio radiation, the radio photons at a large distance, where the photon beam size is small and the scattering is not a problem. Okay. So these are the two places. And it suggests, this very simple argument suggests that it's very hard to produce FRB radiation between 10 to the power 8 and 13 of the neutron star surface due to this enormous, this so-called induced Compton force. Here's the model that we have proposed as to what's going on. There is an analog of a quake or a fracture or settling of the crust that happens suddenly on time scales of milliseconds. And that settling of the crust, which is the outer 1 kilometer of the neutron star, the size of a neutron star, just in case, that needs to be spelled out, is about 10 kilometers is the radius. So this shear wave caused by the crustal break, fracture, some analog of the earthquake on the neutron star, that ripple, that shear wave propagates from the fault line, from the trigger region, and it propagates in this outer crust. And then it couples. That couples and shakes up the magnetic field in the outer, well, in the outside of the neutron star surface. So these field lines are shook up. That's called Alfvén wave. So these Alfvén waves propagate. And in the closed field line regions, these things, the energy is dissipated and produces X-rays and gamma rays. That's the standard model for the soft gamma ray repeaters. The shear wave continuing to move poleward, magnetic pole to be precise, has these disturbances in the magnetic field. So the Alfvén wave traveling to much larger distances and eventually becoming charged star, which simply means that there is too little plasma to be able to support the Alfvén wave. And then these waves are dissipated quickly, quite efficiently, and turned into coherent radio emission. So the coherent radio emission that we see is produced in the region, in the vicinity of the magnetic pole region, but at a distance of hundreds of kilometers or 1,000 kilometers from the surface of the neutron star. So that's the model. There are certain predictions that one can make, straightforward, and in some sense generic, that the maximum luminosity in the radio band should not exceed this number here, 10 to the 47 erg. And the reason for that is that as you increase the luminosity, the electric field strength increases. And when the electric field strength exceeds the Swinger limit, which is this here, 4 times 10 to the 13 ESU, then electrons and positrons are pulled from vacuum. And that cascade of electrons and positrons will short out the electric field, which is needed for accelerating particle to produce coherent radiation. And so that sets the maximum luminosity. There is also a minimum frequency below which you can't produce this coherent radiation, and that's about 100 megahertz. That's causality, or simple causality argument. So let me turn to FRB cosmology for the remainder of the time we have here. What FRBs give us, which is unique, different from any other astronomical source, or almost any other astronomical source, is that we have the column density of electron between the source and us. So this integral of electron density integrated over the propagation path of the photon. And so from there, one can get a census of the baryons in the intergalactic medium, and we should be able to map the hydrogen and helium reionization effect. So this here graph shows the work that was published last year by Meckert and collaborators based on 8 FRBs and their redshift. They could determine, which is shown here. So x-axis is the redshift, y-axis is the DM, the dispersion measure contribution coming from the intergalactic medium. And that means that we have, from the total DM, from each of these bars, subtracted the contribution of the Milky Way, and also subtracted the contribution of the host galaxy. And the host galaxy contribution is highly uncertain. And for these calculations, these people assume that there is a constant contribution to the DM from the FRB host galaxy, and that is taken to be 50 in that astronomer's unit. With that, the residual electron column density is coming from the intergalactic medium, and that is shown here. Each of these colored squares are the DM, IGM, at different redshift. And the diagonal line that you see is what one could expect for the column density of electrons coming from IgM should be as a function of redshift, assuming that the baryon, omega baryon, is as given by Planck 2015 result with a large error bar that you can see here. It's, after all, just a sample of 8 bars. This will get much better. We have some more localization, but many more bars. So this is one result. Now, we suggested a few months ago that FRBs should be able to explore or provide a probe of the hydrogen reionization epoch and also the helium 2 to 3 reionization. And I would like to share that with you. But one thing that I should say something about is whether we expect to see FRBs at high redshift. And there are a number of arguments that there should be FRBs at high redshift greater than 6, because much of the UV photons for cosmic reionization are supplied by massive stars of mass greater than 10 solar mass. About 40% of these massive stars produce magnetars, neutron stars with strong magnetic field, at least in the local universe at redshift 0. At high redshift, the stars are metal poor, faster rotating, and they are more likely to leave behind a rapidly rotating neutron star remnant and a strong magnetic field. And in any case, we know that there are gamma ray bars at redshift greater than 6, including one at a redshift of 9.4. And the GRBs require a strong magnetic field and a compact object, either a neutron star or a black hole. So it's not a big stretch to assume that magnetars and FRB should be there during the reionization epoch, waiting to be discovered. So those are arguments, and we will know in the next several years whether FRBs are there at high redshift or not. The next question is, if they are there at high redshift, can we detect? Can the existing facilities detect? And this graph is to show that, yes, existing facilities can detect fast radio bursts at high redshift. So the x-axis is redshift axis. And the y-axis is the fraction of FRBs. So this is 9 FRBs with known redshift, and what fraction of them, if they were at redshift between 6 and 9, can be detected? The answer is 20% with the current sensitivity of the telescopes that we have. And that is about sensitivity of, in the radio astronomers unit, 1 Jansky millisecond fluence threshold. 20% can be seen. And if the threshold, the sensitivity is improved by a factor of 10, which is totally going to be the case with the upcoming facilities, then 40% of these FRBs, 9 FRBs, can be detected during the reionization epoch. This is simulations of the reionization epoch, where what you're looking at is time going from left to right, earlier time, left, later time, right, redshift, of course, going in the opposite directions, high redshift, left, low redshift. And you can see these patches of reionized bubbles growing in size, and then at a redshift of about 6, the entire universe is reionized. So it's a patchy, bubbly epoch of reionization. And that would be difficult to understand these bubbly, patchy would be very difficult. But what one can hope to do is understand a average at a fixed time slice of the spatial hypersurface, average ionization, and how that changes with redshift. And that's what is shown here in this graph to the left. That is the ionization fraction of the universe, to be precise, the number of electrons per baryon on the y-axis, and redshift z on the x-axis. This is the solid line is an empirical model taken from a work of Robertson et al. That is combining a number of different observations and the data, Planck included, and plus many other astrophysical proofs like Lyman alpha, quasars, and so on. The dotted line that you see is just a model, simple model made up, which is different from Robertson et al., to show that these two different reionization histories can be explored and distinguished by using FRBs in the following way. So to the right, this graph here shows the DM of FRBs at different redshift. So there is almost a linear increase to the DM at low redshift, and then it starts to plateau at high redshift during the reionization. When going at higher and higher redshift, the universe is turning more and more neutral, which means that the number of electrons per unit volume is, well, not per unit volume, but per baryon is decreasing. And once we are past at high redshift, when the universe is neutral, then we have no electrons, and the electron number, the number of electrons between the source and us plateaus. And that's what we are seeing here. At high redshift, there is this plateauing due to the universe becoming neutral. And you can see that there is a difference in these two different reionization histories. In this dotted line, the maximum DM is larger than this Robertson et al. Reionization history of the universe by about 500 parsec per cc. And if we can determine the FRB DM, or the maximum DM for FRBs, to 500 in the same units or better, then we can do better than the Planck 2020 Thomson optical depth result. That's shown here. X-axis is Thomson optical depth. Y-axis is the DM of FRBs, and the shaded region is consistent with Planck 2020. So this is the region, this Thomson optical depth consistent with Planck 1 sigma result. And you can see that range of optical depth consistent with Planck has a spread in the DM max of about 600 parsec per cc. So by making a measurement of DM max of the FRBs to better than about 500, one can do better than the Planck 2020 result. This is same thing showing in the terms of individual, well, in an ensemble of reionization histories. So each curve that you see is one particular reionization history of the universe, right? And the gray curves are all different reionization histories consistent with the Planck 2020 data. The black curves consistent with the Planck data, and further more constrained by the DM max of the FRBs when we see it. Can we determine FRB DM max to an accuracy of 500 parsec per cc? This graph shows that yes, it's doable, because the contribution of the host galaxy of FRBs at high redshift declines as 1 over z. And so the contribution of the host galaxy of the FRBs at high redshift is of order 100 or less. And that is coming from cosmological simulations. This one is fire simulation. The fluctuating electron density in the intergalactic medium is another problem in determining DM max to high accuracy. This one shows that according to the illustrious cosmological simulations, the contribution of the fluctuating part of the intergalactic medium is order of about 250 parsec per cc. Combining the two together is still less than 300 parsec per cc. So one should be able to achieve that accuracy of 500 or better. This is another way that one can determine the reionization history of the universe, but without using the redshift of the burst. This is without redshift of the burst. One can take the number of bursts in DM bins, and then by looking at the number of bursts in different DM bins, as a function of DM, one can tell apart different reionization histories. In the last...
Okay, this is the last, because I forgot to give you a 5-minute warning. So now it's...
This is the last slide.
Okay, perfect.
This is the last slide. And this is simply to show that FRBs potentially can also be useful for helium reionization. Helium singly ionized to doubly ionized helium can be explored. Not easy, it will be difficult. And these are two different helium reionization histories. You can probably just barely see these two different curves, black and red. And they are corresponding to helium reionization at slightly different redshifts. But you can tell them apart when you have about 1,000 FRBs, but with known redshift, between redshift of 3 and 6. With that, let me leave the summary slide here and take questions. So this is it. As I say, the summary slide is here, and let's take questions. So thank you for your patience.
Thank you very much for this very interesting talk. Okay, so we have 2 questions. Francesca?
Yes, thank you first of all for this very nice overview of the field and for your results. If I understand correctly, you were focusing mainly on repeating fast radio bursts, but what about the non-repeating, and what is the sense currently in the community about whether repeating and non-repeating can be originated by 2 different populations? What's your opinion?
Certainly. So let me address in the order that you asked the question. Much of the result that I showed about the cosmology is for non-repeating bursts. Okay, so they are not for repeating. Yeah. Okay, so that's the answer to your first question. The second question, whether there is a difference between the physics and the astrophysics of repeating versus non-repeating. The evidence at this point is not sufficiently clear. That is to say, there are certain lines of evidence suggesting that maybe they are coming from different kinds of objects. It's still magnetar, which means neutron star with a strong magnetic field, but some difference in the kind of magnetar that is producing repeating versus non-repeating bursts. And the lines of evidence is the nature of the host galaxy, where these things reside, the polarization measurement, the duration of the burst, etc. Yeah, but I would say that on the whole, the evidence is not so clear-cut that there is a distinction between the 2 populations. And what appears to be non-repeating FRB, I think is more a question of the frequency of repetition, which means the following: all the ones that we call non-repeating, is simply will turn out to be, in my view, and I can give you very good arguments why, they will simply turn out to be repeaters, but at low frequency, which means they stay dormant for a period of a year or two, meaning they don't repeat on a period of a year or two, but they repeat on a longer time scale. And the reason for that they all non-repeaters got to be, or almost certainly are repeaters, is just the number of these events. If they really are one-off, meaning they never repeat, there are too many of them, few thousands a day. And that exceeds the number of catastrophic events. Yeah, that almost is order of the number of supernovae per day. Okay. And we have we have good arguments, good evidence that typical supernova doesn't produce FRBs, and so on. So in any case, that's kind of those are the, well, answers to your questions. I don't know if you have a follow-up question.
I do, but I leave this for the discussion.
Elias, question?
I'm sorry for the very naive question, but why we didn't see these FRBs, let's say before 2004 or 8, I don't remember. Is it because we were not looking for them, or we didn't have the means to detect them?
Okay, so right. So the discovery in 2007 was analysis of the data that was collected 7 years ago. So just a clarification. So the data was collected, and yeah, so basically people were not looking for it.
Okay.
And it could have been detected. Surely it could have been detected if people had, looked for it in 2000, and maybe a bit earlier.
I see. And what is the farthest FRB that has been detected so far?
In the terms of the actual redshift measurement, I would say redshift of about half, just about that. But based on the DM, the electron column density, and taking that as a reasonable estimate to within an error of maybe 15-20%, well, more like 20% error, I would say maybe about redshift of 1.5, maybe closer to 2, I would say.
Okay, thank you very much.
Norma?
Thank you very much for this very clear, and instructive pedagogical lecture. I would like to know about, instead or besides neutron stars, if you consider two black holes, and in that case, in all these bounds you need for strong magnetic fields bigger than the figure there, 10 power 14. How much could be higher these magnetic fields in order to perhaps have other signatures of other insights in other wavelengths? And that's the first point.
So there are several questions in there regarding binary black holes producing. So I'm assuming that you mean binary black holes, but the black holes are like stellar mass, like, few times the mass of the sun, not millions of times the mass of the sun, right?
Yes.
Is that correct? Yes.
It's that right, but the mechanism you are invoking here could be also applied,
So
for
the problem,
supermassive black holes too. But of course, you can go with the stellar mass black holes.
All right, so let's take the stellar mass binary black hole. The problem is it will not work. And let me tell you why it will not work. If it is just a binary black hole, and no accretion disk, no plasma, then there is no mechanism there to produce any electromagnetic radiation. So you need plasma and you need a strong magnetic field. And so these binary black hole would need to be embedded in plasma, and then we should see some other radiation. Yeah, if there is a plasma,
Yeah.
black hole would be accreting the plasma, and there is radiation associated with this process of accreting plasma.
Yes.
And they are a very good limit, at least for some cases, quite good limit. So that's the problem. So you will need binary black hole with good plasma density, sufficient plasma density and very strong magnetic field. And then you should see signature of that in other wavelength band, X-ray. And we don't seem to see that. And I guess the second question is in a sense related to this one here. You asked, do we see radiation in any other part of the electromagnetic spectrum? The answer is that the burst that was in our galaxy, we saw X-rays. Okay, accompanying the radio with a slight time difference of about a few millisecond time difference between the X-ray arrival and the radio arrival. But other than that, we have no other case of a FRB where we see radiation in any band other than the radio band. Does that answer your question, or you had something else in mind?
Yeah, it's your answer is very good for me. And I also thinking in terms of, because of supermassive black holes, also there are all these plasma, I mean, the conditions and the strong magnetic fields. And it could be possible to, I mean, I assume there will be also this generation, even, I mean, that I would like to see your comments about that.
Okay, certainly. So I would say that is very unlikely.
I think we should probably postpone this to the discussion session, because I think people need a break before the next session. So I would suggest that we stop here for the break, and then we will resume in 5:30 Paris time. And all these further questions can be discussed in the discussion session later, which will be on FRBs.